Welcome to Advanced Calculus Real Analysis Lecture 7, the Sequential Compactness Theorem, Section 2.4 of the text Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert, Eyabi. In this section, we would cover the Sequential Compactness Theorem, which identifies an important property of the set of real numbers R that is used to prove fundamental properties of continuous and differential functions. Subsection 2.4.1 definition. Let An be a sequence and let Nk be a sequence of natural numbers that is strictly increasing. That is, N1 is less than N2, which is less than N3, and so on and so forth. Then we can define the sequence Bk by Bk equals Ank for every integer k, and we call Bk a subsequence of the sequence An, and we would denote Bk by Ank. So Ank is a subsequence of An. Okay, let me explain this with an example. Let An be a sequence. N is from the set of natural numbers. So n is 1, 2, 3, 4, 5, 6, and so on and so forth. Now, let's consider a sequence of the set of natural numbers 2, 4, 6, 8. So this is a sequence of indices. In this example, our n1 would be the natural number 2, our n2 would be the natural number 4, our n3 would be the natural number 6, our N4 will be the natural number 8, and so on and so forth. You see that N1 is strictly less than N2, which is less than N3, which is less than N4. So this sequence is strictly increasing. Now I'm going to define another sequence whose indices would be the Ni's. Define Bk to be A2k. So our Nk is 2k. So the terms of the sequence An are A1, A2, A3, and so on and so forth. And the terms of the sequence Bk, which is Ank, would be A2, A4, A6, and so on and so forth. So we can see here that Bk is a subset of An. All the terms in Bk are also terms in An, but there are some terms in An which are not in Bk. So Bk is a subset of Ank, or in general, we say that Ank is a subset of An. Ank is a subsequence of our sequence An. And also quickly observe that Nk is always greater than or equal to k for every k. Now let's give an example of a sequence An and then give examples of subsequences of our sequence An. So define our sequence An by An equals 1 over n. N is a natural number. Then consider the sequence Ank, which is actually A2n, as 1 over 2n. You can quickly see that all the terms in Ank would also be terms in An. So Ank is a subsequence of An. Similarly, 1 over n cubed plus 3 is a subsequence of our sequence. This is also a subsequence of our sequence. As a matter of fact, I could define Ank to be 1 divided by pi times n. This is also a subsequence of our sequence. So that is how we define a subsequence of a sequence An. So quick question. If a sequence An converges, does it necessarily imply that if Ank is a subsequence of our sequence Ank would also converge? Let's even go further. If the sequence An converges to a number A, can we conclude that Ank also converges to the same number? So we have two questions in one. If An converges to the point A, number one, if Ank is a subsequence of An, does Ank converge? If it converges, would it have to converge to the number A? Now, let's rephrase this. When we say An converges, what we are saying is that for every epsilon greater than 0, I can always find a natural number n such that the absolute value of an minus a is less than epsilon whenever n is greater than or equal to uppercase n. If this holds, can we conclude that the absolute value of ank minus a would necessarily be less than epsilon for every n greater than or equal to uppercase n? And the answer is yes. In other words, if an converges to a, then every subsequence of an would converge and also converge to the same point a. We would look at this a little more rigorously in just a few minutes. But before we get there, let's look at this picture. So that's an and that is a. That's ank. The absolute value of an minus a, that's the distance between an and a. And the absolute value of ank and a is this distance right here. So as this distance gets really small, less than epsilon, it is expected that this distance would also get very small, less than epsilon. Indeed, the absolute value of ank minus a is less than or equal to the absolute value of an minus a for every n greater than or equal to n, and the absolute value of an minus a is less than epsilon, so we can deduce that the absolute value of ank minus a is less than epsilon for every n greater than or equal to n, and that is strict less than, not less than or equal to. Sorry about that. So if an converges to a, ank would also have to converge to a. We will look at this a little more rigorously right now. Subsection 2.4.2 proposition. Let an be a sequence that converges to the limit a. Then every subsequence of an also converges to the same limit. Interesting. Proof. Suppose an converges to a. Let ank be an arbitrary subsequence of our sequence an. We must show that ank converges to a, i.e., let epsilon greater than 0 be given. We want to find a natural number n such that the absolute value of ank minus a is less than epsilon for every n greater than or equal to n. Now, epsilon greater than 0, an converges to a, implies that we can find a natural number uppercase n such that the absolute value of an minus a is less than epsilon for every n greater than or equal to uppercase n. But we do know that ank is a subsequence of an, so that means the absolute value of ank minus a is less than or equal to the absolute value of an minus a. But the absolute value of an minus a is less than epsilon for every n greater than or equal to n. So following this chain of inequalities, we can say that the absolute value of ank minus a is less than epsilon for every n greater than or equal to n. In other words, ank converges to a, and we are done. Now, ank could be an plus 1. This is going to be a subsequence of an, and this is very important. So if the limit as n approaches infinity of an equals a, we would expect that the limit as n approaches infinity of an plus 1 is a. It's a very simple observation, but when dealing with the convergence of recursive sequences, this becomes very important. Okay? So the big thing here is that if a sequence converges to a point, then every subsequence of that sequence will converge and will converge to that same point. Subsection 2.4.3 theorem. Every sequence has a monotone subsequence. That's interesting. So a sequence may not be monotone, but it is guaranteed that the sequence would have a monotone subsequence, and we shall see the importance of this as we move forward with this class. Now let's go ahead and prove it. Proof. Let an be a sequence where n is a natural number. We call an index m a peak index for the sequence an, provided that an is less than or equal to am whenever n is greater than or equal to m. So m is a peak index. Now, Either there are only finitely many peak indices for the sequence AN, or there are infinitely many such indices. Now let's investigate both cases. So right here we have AN and we have AM. So AN is less than or equal to AM if N is greater than or equal to M and M is a peak index. So case 1, there are only finitely many of such indices. Then we chose an uppercase N such that there are no peak indices greater than N. We will recursively define a monotonically increasing subsequence of our sequence AN. So that is our goal. We want to recursively define a monotonically increasing subsequence. And in the next case, we would want to define recursively a monotonically decreasing subsequence of our sequence AN. And therefore, we would conclude that whether it's case 1 or case 2 that holds, there is always a monotone subsequence of our sequence. Okay, let's proceed with case 1. Indeed, define N1 to be uppercase N plus 1. Now, suppose that K is an index such that positive integers have been chosen such that AN1 is less than AN2 is less than ANK. Now, since NK is greater than N, uppercase N, the index NK is not a peak index. Recall that we did choose our N such that there are no peak indices greater than uppercase N. Hence, there is an index nk plus 1 which is greater than nk such that ank plus 1 is greater than ank. Thus, we recursively define a strictly increasing sequence of positive integers nk having the property that the subsequence ank is strictly increasing. And that takes care of case 1. For case 2, there are infinitely many peak indices. For each natural number k, let nk be the kth peak index. Now, directly from the definition of a peak index, it follows that the subsequence ank is monotonically decreasing. So whether it's case 1 or case 2 that holds, a sequence an always has a subsequence ank that is monotone. Here is a very simple exercise for you. I want you to give me an example of a sequence that is not monotone, and also go ahead and find a monotone subsequence of your chosen sequence. Now, do not forget that this entire section deals with the sequential compactness theorem, and we have not yet stated the theorem. We have seen some very nice results, but we have not yet stated the sequential compactness theorem, so we're getting there soon. Subsection 2.4.4 Theorem. Every bounded sequence has a convergent subsequence. Did you catch that? Recall that right from the very beginning of chapter 2, we did prove that every convergent sequence was bounded, but not every bounded sequence was convergent. Now we are saying that though every bounded sequence is not convergent, we actually do have a theorem that relates boundedness and convergence. And the theorem is that every bounded sequence has a convergent subsequence. Okay, let's go ahead with the proof. Let AN be a bounded sequence. We have to prove that AN has a subsequence ANK that is convergent. Now, by the theorem we just saw, theorem 2.4.3, we can choose a monotone subsequence of our sequence AN and call the monotone subsequence ANK. Now, if AN is bounded, then it is expected that its subsequence ANK would also be bounded. So ANK is a bounded monotone sequence. And by the monotone convergence theorem, the subsequence ANK converges and we are done. So every bounded sequence has a convergent subsequence. Interesting. Let's keep going. We are approaching the core of section 2.4, the sequential compactness theorem. So let's go ahead and take a definition. Subsection 2.4.5. So what we're saying is that if S is a subset of the set of real numbers, then S is said to be sequentially compact if for every sequence in S, I can always find a subsequence of that sequence such that the subsequence converges, and it converges to a point A, which is also an element in S. If that happens, then S is said to be sequentially compact. Recall that we are not talking about the convergence of the sequence A itself. We are simply saying that A must have a subsequence that is convergent, and the subsequence would have to converge to a point in S. If that holds, then we say that S is sequentially compact. Now let's look at a few examples. Subsection 2.4.6, example 1, consider the set S closed at 0, open at infinity. Now define the sequence an equals n. Then this sequence is clearly in S. Now by the Archimedean property of the set of real numbers, every subsequence of an is unbounded from the way it is defined, and therefore it fails to converge. Okay? Thus, S is not sequentially compact. Recall, for S to be sequentially compact, then every sequence in S must have a subsequence that converges to a point in that set. But we have defined a sequence an equals n, and all subsequences of our sequence are unbounded and do not converge. So we have not found a subsequence that converges to a point in S, and therefore this interval is not sequentially compact. Example 2. S is the interval open at 0 and closed at 2. Now let an be the sequence defined by an equals 1 over n. Then the sequence is in S. 1 over n converges to 0. We saw that in section 2.1. And we did prove that every subsequence of a sequence converges to the same limit that the mother sequence converges to. So if 1 over n converges to 0, every subsequence of 1 over n would also converge to 0, and 0 is not an element of our set S. Therefore, for the sequence 1 over n, we have not been able to find a subsequence that will converge to a point in S. Therefore, S is not sequentially compact. Now go ahead and investigate these other sets and tell me whether these sets are sequentially compact or not. These examples would lead us naturally to the Sequential Compactness Theorem, which is our main theorem for the day, with amazingly an interesting short proof. Subsection 2.4.8 Theorem, the Sequential Compactness Theorem. The big theorem of the section, with amazingly a very simple statement. Let A and B be real numbers such that A is less than B, then the closed interval AB is sequentially compact. That's it. i.e., every sequence in the closed interval AB has a subsequence that converges to a point in AB. So there are two things we want to look at here. Number one, we have to show that every sequence in the closed interval AB has a convergent subsequence, and we have to show that the limit of that subsequence is in AB. Let's go ahead and do that. Now let A and B be real numbers such that A is less than B, and let AN be a sequence in the closed interval AB. Then AN is clearly bounded. But we saw in theorem 2.4.4 that every bounded sequence has a convergent subsequence. So if AN is bounded, then AN has a convergent subsequence, and that takes care of the first part of the proof. Every sequence has a convergent subsequence, and all we are left to do is to prove that the limit of that convergent subsequence is also in AB. Now, The sequence AN is a sequence in AB. Therefore, the subsequence ANK is also a sequence in AB. AB is a closed interval, and in previous lectures we did prove that if AN is a sequence in AB that converges, then it must converge to a point in AB. Go back and look at previous lectures. So ANK is a subsequence of AN that is convergent and is also a sequence of the closed interval AB, and therefore we can conclude that our limit of convergence is an element in AB. So we have shown that every sequence in AB has a convergent subsequence, and we have shown that the limit of the subsequence is an element in AB, and we just proved the sequential compactness theorem. Very short, elegant proof, but do not forget there are so many other theorems we have used in the proof of theorem 2.4.8. And before we close this section, we just want to inform you that the sequential compactness theorem is also known as the Bolzano-Weierstrass theorem. So if you pass somewhere and you hear some people talking about the Bolzano-Weierstrass theorem, they are talking about the sequential compactness theorem. The closed interval AB is sequentially compact. That brings us to the end of section 2.4 sequential compactness theorem, and I will see you in lecture 8. Thank you and God bless you.